Hi, I'm Luigi Viespoli and I am a PhD student at the Norwegian University of Science and Technology. The work I'm about to present is a simple iterative methodology for evaluating the impact of creep damage under fatigue loading. The presentation will go through the motivation for such a formulation, the idealized concept behind it, the alloy adopted as example for the verification of the method and its properties in terms of creep, fatigue, and cyclic behavior. The results and main conclusions will then be summarized. When a metal is subjected to repeated deformation in high temperature conditions, time-dependent deformation mechanisms are activated. Creep deformation contributes then to procure damage to the metal lattice and boundaries and severely reduces the fatigue life of a component. Characterizing the material fatigue response at an array of temperatures requires extensive fatigue testing, which could be reduced with the use of an opportune failure criterion. The logic of the method consists in an initial characterization of the material in terms of creep damage, cyclic response, and fatigue at the reference temperature. The data are then combined to shift the fatigue curve proportionally to the amount of creep damage induced. The alloy used as study case is the nickel-based superalloy Heinz 230. It is a commercial alloy used in a range of applications in which temperature and corrosion resistance are of paramount importance, and used to produce components by plastic deformation or casting. The specimen used to generate the results reported in this study have been manufactured by rolled plates. We can now start to analyze the various components of the damage criterion. The first point is that it is necessary to quantify the damage introduced by creep. Two of the simplest formulations, conceptually based on Miner's damage summation rule, are the time fraction rule and the creep ductility exhaustion rule. The time fraction rule, for which the damage is quantified as the ratio between the permanence time at the given stress and the rupture time at that stress, will be used in the following in integral form, adding the contribution of each infinitesimal instant during the uploading phase of the fatigue cycle. The manufacturer of the alloy reports in tabular form a fitting of the creep data. These are presented as the stress to generate a deformation of 0.5%, 1% and failure in a time of 10, 100, 1000 and 10,000 hours at temperatures between 649 and 1149 Celsius degrees. It is evident the impact of temperature and stress on the time to failure. All data can be displayed in a single function using the Larson-Miller parameter. Such parameter correlates the creep life with time and temperature. The formulation includes a material constant C, which is equal to 20 for most metals. It can be seen that all results at different temperatures are well correlated in terms of nominal stress versus the Larson-Miller parameter by an exponential relation. Such relation will be used to compute the time to pure creep failure for each load instant during the fatigue cycle. The manufacturer reports also the results of a series of strain-controlled fatigue tests at temperatures between 427 and 982 Celsius degrees. These were tested at the frequency of 0.33 Hz, that is 20 cycles per minute, at a displacement ratio of -1. The detrimental influence of temperature on fatigue performance is evident. The fatigue curve at the lowest temperature is taken as the reference curve for the extrapolation. The Smith-Watson-Topper equation is calibrated on the base of this curve and will be used as starting point for the generation of the array of curves at higher temperatures by reducing the strain amplitude at any given number of cycles according to the computed creep damage. The last necessary set of data is constituted by the cyclic response of the material. It is in fact necessary to know the stress that will be reached at any strain amplitude in function of the temperature and strain rate. In the literature are available a series of results of cyclic testing of highness 230 under the same conditions of strain rate and temperature at which the fatigue tests reported by the manufacturing were executed. The alloy experiences cyclic hardening, and the stabilized form of the hysteresis cycle has been considered to correlate strain and stress in the integration of the creep damage. This is the organization of the extrapolation method in form of the equations used. The procedure is the following. The creep rupture data are summarized in terms of Larson-Miller parameter, equation 1, and correlated to the nominal stress, equation 2. Equations 1 and 2 are then combined to correlate temperature, applied stress, and creep time to failure, equation 4. From the cyclic testing, we are able to correlate the stress with temperature, frequency, and strain amplitude, equation 5. We recall the time fraction rule for the computation of the creep damage, equation 3. By combining equations 4 and 5 into equation 3 and writing it in integral form, that is the addition of all the infinitesimal creep damages introduced by all the stress levels reached in the loading during the cycle, we obtain equation 7. For simplicity, since what is considered in the procedure is the ratio between the creep damage at different temperatures, the integration is done on an ideal upload from zero stress and zero strain to the amplitude stress and strain. For this reason, the time of the integration goes from 0 to a quarter of the period of the fatigue cycle. Equation 6 gives the strain amplitude for any number of cycles at a reference frequency and temperature. The strain amplitude at a different temperature is finally computed with equation 8. This requires a series of iterations. An array of number of cycles is chosen, and for each of these, the strain amplitude at failure in the reference conditions is computed with equation 6. The creep damage for each of these points is computed with equation 7 at the reference conditions and at the temperature at which we want to obtain the extrapolated fatigue curve, but using the reference strain amplitude as first approximation. Equation 8 is then applied, multiplying the strain amplitude at the reference conditions by the ratio between the logarithms of the creep damage of an ideal upload at the desired and reference conditions. It is evident that the creep damage at the new temperature T has been overestimated, since the first approximation strain amplitude is at the reference conditions and higher value than the target. Assuming that the reference temperature is lower than the target temperature T. This will generate a strain amplitude which is lower than the correct one. This new strain amplitude is then fed into equation 7 for the computation of the creep damage at the temperature T, and the operation is repeated until convergence is reached. Finally, we have obtained the results of the procedure. On the plot on the left, we can see the experimental fatigue results, each well matching the relative extrapolated curve, represented by a continuous line. The plot on the right shows how the experimental and predicted strain amplitudes for any number of cycles are included in a scatter band of ±20%. Concluding, the methodology presented, which requires a first characterization of the material in terms of creep life, cyclic response, and fatigue at the reference temperature, has produced accurate results in the case presented. In theory, it should be able to account for the impact of a modification of the strain rate as well, but this has not been experimentally proven so far. In case it should be verified, it would be a great advantage for the prediction of fatigue life at the low strain rates, for which fatigue testing results extremely time-consuming and sometimes unfeasible. Thank you for your attention.